So the code for the phase 3.0 multicast with no ordering is like this. I have some this is the main function down there, their main function. And then I create a socket, and then we should use a socket datagram. And then I configure the socket operations, reuse address and reuse ports. And here are some parts I call my helper functions to help me to control the process. So we'll ask user input how many process amounts they will create, and we will remind them they must follow the amount they input. And this is, so this one, we will write the amount the user declared into the file, the process amount declared file. Let's have a look. It will be always 0 at the beginning, because when we stop the process, I will clean it to 0. And then each time when user create a new process, we will count the counter, the process counter will increase by 1. I also have a signal handler function, signal capture function to capture some like Control-C signal. So once the Control-C signal is captured, it will clean those process counter. It will clean the declare process amount files before they really stop this process. So if you use Control-C to stop this process, it will be fine, it will be handled. And then I have a while loop, which is used to count, to monitor how many processes you have created. Only when the declared process amount is same as the process counter, we will continue the below parts. It's the ordering parts, but of course we don't have ordering here, just sending some message, multicast some message. This is the data structure we used to store local clock vectors, which is a vector. It has not only the local clock value, but also the knowledge of the clock values of other nodes. And then we just create a thread of sending part and receiving parts to send and receive message. So this part is that I didn't change the same as previous phase. I just use the same socket field descriptor, and we need to pass the local clock vector. We need to use that, and then the IP protocol options, multicast time to now, multicast interface, and then send message. I use a for loop to send out 10 message to multicast to message. Receiver part is the same as previous phase. So we use the same socket field descriptor, and we band it. We change the IP, so the IP options. We need to join the multicast group, and then we can receive message. That's it. So I think I can run it to show you. If you haven't made, you need to make, because I have made, so I don't do that anymore. I just run it. This is the first process, so it will ask me how many processes you declare. I will say like 3. And then it will count how many process running. So here is the while loop part. It's waiting for only the process counter equals to the process amount you declared. It will continue after that. So in the second terminal window, I run the second process. So there are 2, but you declare 3, so they are not equal. They are not still in the while loop. And then I create the third process. And then they will meet the condition that process counter equal to the declared process amount. So it will multicast 10 message, each of them. The first process, it will multicast 10 message. The second process, it will multicast 10 message. And the third process, it will multicast 2 messages. And we say the local clock vector of first process is correct. So this is its own local clock value. This is first process knowledge of second process clock value. It's correct. This is a first process knowledge of the second process clock value. It's also correct, and they are same, and they are same. They are all correct. So this is a 3.0. I will stop there. So each time when I Control C, it will capture my Control C signal and clean the process counter and declare the fire. And then is phase 3.1, I implemented the FIFO ordering. So you see in the phase 3.0, I already done the data structure we need, and some helper function we need, and the multicast message works well, receiving multicasted messages works well. So on top of that, I implemented the FIFO ordering in phase 3.1. So actually the difference is that the message structure is different. For FIFO ordering, the message we send out is just its own clock value. Someone call it the sequence number. It's just its own clock value. That is to say, like this. Hey, I'm process number 2, and my local clock is 5. This is different to casual ordering. So pay attention to this. And receiving, when you receive multicasted messages, the process will only update the knowledge of the of that process. So if the receiver receives this message, for example, let's say the process number 3 receive this message, the process number 3 will only update the knowledge of clocks of process 2 to 5. It doesn't change the knowledge of clocks of other processes. It only updates the knowledge of the clock of process who sent it. And this is a FIFO ordering. So let me compare with the casual ordering. For casual ordering, the sending message will be different. It will send the whole clock vector. The whole clock vector, as we declared here, the whole clock vector. This is casual ordering. What it will send? It will send it will multicast to all process the whole clock vector. It including its knowledge of others. So let's say the example, there are 3 processes. If I am process number 2 and my clock vector is 253, and we can know only this one is 100% sure correct. The 2 is just my knowledge of node 1's clock value. The 3 just my knowledge of node 3's clock value. The 2 and this 3, they might be wrong. Only this 5 is my own clock value. Only this 5 is 100% correct. So in this example, the message will send be out is like this one, like the whole clock vectors. Compared to the FIFO ordering, the message is sent out is just its own clock. This is different. And after receiving a message, the cache ordering also different. That after receiving the message, it will update its knowledge of the clock of that process. So who sent the message, I will update my knowledge of the sender's clock. And our same example like this, when I receive this message, I will change my knowledge of second process to 5. But there are one more difference that is so the same part is I only update one clock knowledge. The different part is the requirement is stricter. The requirement is that the one more requirement is that it's asked for checking the received all other process clock except 2 process, except the received process and the current process. If you want to know more details about this, you should go to review the updating rules of casual multicast. It clean so this picture it explains it better in the mathematical language. And let's go back to the coding details. So I mean the different parts with FIFO ordering is that the requirement is stricter. It has a second requirement that it will check the received or others, and it should be bigger than your local. Okay, and then let's show you the codes of this part. So first, let's go to phase 3.1. It's FIFO ordering. The updating rules is simpler than the casual ordering. So the main function is same. I didn't change much for the main function. It will exactly same. So build the socket and change the configuration, and then some helper method I use to control those process. And one more thing is buffered message and delivered message. There are 2 more data structures we need. I think I mentioned them. Where are they? Here. The buffered messages and delivered messages. For both FIFO ordering and casual ordering and total ordering, they all need these 2 data structure. That is, if the message I received, if it meets the updating requirement, I just deliver that message. So in the coding, I just put it into the delivery message variable, this vector. If it doesn't meet the updating requirement, I will buffer it first. And then later, whenever it meets the updating requirement, I will move it from buffer to deliver it. So these 2 structures, they are needed by all those 3 ordering algorithms. And one more thing that I want to highlight is that each time a new message is delivered, you need to check the whole buffer, the whole message buffer to see, is there anyone meets the updating requirements, because each time you merge, you deliver a new message, the clock value changed. So that's possible. One of those messages in message buffer will meet the new condition. In the new condition will meet the updating requirement in new condition. So each time a new message is delivered, you must check the whole message buffer. Yeah, that's the preparing work we need before we start the two process. So this are just two process we did, and sender and receiver. Two threads, so two threads. And the sender will be similar. So I want to mention that before I send a message, I ask it to sleep 2 seconds because I needed to make me to have time to run or to set up all three process and needs the three process. So let's go to the correct directory. Yes, this is the 3.1. This is FIFO ordering. If you haven't made, you need to make. Okay, so then we run the first time when we set up the first process, it will ask how many processes you want to create, and let's input 3. And the process counter will count how many processes are running. We have only one process, the first process, and here. Let's also change to the correct directory and run it. It will be a second process, and the process counter will update to 2. And then here is for the run 3.1 and run 5.4. So after I push this enter, it will be 3 process, and it will the process counter equal to the declared process amount, and then it will begin the multicasting steps. What happened? Wait a moment. Okay, so after I push this enter button, the third process will be created, and it will meet the requirement that process counter equal to the declared process amount. It will start multicasting. So let's push the button. Okay, so they start, and they all start, and they work well. In the standard for loop, where I think I have 10, the for loop of 5, for loop of 5. So let's wait for all those 5 messages have been finished. Okay, so they finished. All process will multicast 5 messages. So process 1, it will multicast 5 messages. Process 2, it will multicast 5 messages, and process 3, it will multicast 5 processes, 5 messages. Let's see what they read. Let's go up a little bit. Let's go to the first message. It will be longer. It will be none. Okay. So here they are still waiting, and after I build the third process, it will begin multicasting. Here it begin the multicasting. It tell you it's number 1 process, and receiver start, and the receiver process ID is blah blah blah, and the receiver thread ID is blah blah, and the sender process ID. They are in same process, so it's the same process ID, but it has separate thread ID that different. And go down a little bit. So when they start, the local clock vector of process one is 000 because nothing happens because no message has been sent. Each time it sends a message, it will increase its local clock by 1. So first the message is sent. I print out after a message is sent, it increases itself. It increases its own clock value by 1. So the clock vector is 1 or 100 at this moment. And then it received. This message is, so you can read my message. The first 2 variables, they are 1 and 1. They are my local clock value and my process number. That means process number 1 send this message, and the process number 1 say my local clock value is 1. And after I receive message, I need to split it. This is some message processing. Actually, we don't need to print this out. And because this message comes from itself, so we don't need to do anything. We don't need to upload any knowledge of clocks of other nodes, because when it sends out the message, it already increases its own clock by 1. So that's the first message. And then we receive one new message, that is process number 3 said process number 3's local clock value is 1. Okay, we got it, and we receive this message, and we need to check whether this condition meets the updating requirement. So the updating requirement for FIFO is simple that let's go up to here. Is if the PJ process J sequence number S, that is the number we received, equal to my local knowledge of process J's clock plus 1. So for process 1, its knowledge of process 3's clock is 0. This is process 1's knowledge of process 3's clock. And the process 3 sent a message said, hey, my new clock value is 1, and this 1 equal to this 0 plus 1. So that means it meets the updating requirement. Then process 1 will deliver this message and update its knowledge of process 3. It will update this 0 to 1. So it is a message delivered, and here I print all delivered message and update the clock vector in process 1. It update this value to 1. And I print all buffed message, but here the message buffer is empty. And this is not necessary to print this message, because we didn't read any message from message buffer, so we didn't update the local clock vector from message buffer. And then we receive a new message, that is process 2 say, hey, my local clock is 1. And we also need to check whether it meets the updating requirements, and it did, because the process 1's knowledge of process 2's clock is 0. And process 2 say, hey, my new clock is 1. And this 0 plus 1 equal to this 1. So it meets the updating requirements. So the process 1 update this 0 to 1. It will update. This is a new message. This is an old message keyword. It will update the middle 0 to 1. And also here, we check the message buffer, but then no message in buffer. That's not also no new update. No new update. And then the process 1 send its second message. After it sent a message, it increased its own clock by 1. So the first element become 2. And the receive message, because this message comes from the process 1, that means it receives the message itself sent out. So nothing to do. And then receive a new message that process 3 say, hey, my new clock is 2. And that's the knowledge of process 3 is 1, but process 3 say, hey, I'm 2. So this 1 plus 1 equals 2. That means it meets their updated requirements. So it just updates. So deliver a message, update to 2, and the message buffer is also empty. So no updates after checking message buffer. And then read a new message that the second 2 say, hey, I'm 2. So it will update this 2 to 2. That's it. And continue. And finally, the local clock is 555. And all those other processes, they do the same thing. So the final value they have is 555, and they are all 555. They work correctly. And then I want to simulate the situation that one message may be lost. Let's say the failure situation, what will happen. So if you want to do that, there's one simple thing is that you just comment this code, this line, and it doesn't wait for 2 seconds, and then when we run the first process, second process, third process, it doesn't wait anymore. So sometimes the first message is a multicast. Someone cannot receive it. Let's do it. Let's make it again. Okay, and let's run the FIFO. Let's say we want 3 process. This is the first one. This is the second one. And then I will do a third one. As I mentioned, we don't wait for 2 seconds anymore. So it's highly likely some of them cannot receive the first multicast message. Let's see what will happen. I will click the enter button. Oh, you can see that. Let's wait for it to finish 5 messages. Okay. So as I said, all of them multicast 5 message. Process 1 multicast 5 message. Process 2 multicast 5 message, and process 3 multicast 5 messages. But we can see here the final clock vector of process 1 is 505. That means the process 1's knowledge of process 2's clock is 0. This is wrong, but because we know the second process no clock is actually 5. Now, why this happened? Let's go back to the first message. You will see what it happened and why it happened. So this here they are in the while loop to waiting for 3 process created, and here it begins the multicasting, and its local knowledge is 0, 0, 0. So it received the first message. It comes from itself. That process 1 say my no call clock is 1, because this message comes from itself, so no action created. And then it print out the message sent, the first message sent. So this is actually it's the order, the printing order is wrong, because this one it must happen first, because you and then you receive the message. This is of course so the sender, the sending thread broadcast this message first and increase its local clock by 1, and then the receiving thread can receive it. So this is a printing issues. But it doesn't affect the true value of the clock vectors at process 1. And then the process 1 receives one new message that says process 3 say is no call clock is 1. So we check my knowledge of process 3 is 0, but the new message says 1, and this 0 plus 1 equal to this 1. So that means it meets the updating requirements. So it will update this this knowledge of the process 3. And it say, hey, message delivered, and updated this to 1. And it checks the buffer, message buffer, but it's empty. So nothing updated from message buffer. And then it receives a message from process 2, say, my clock is 2. Process 2 say my clock is 2. So did you realize what happened here? That is process 2. Let's go check the process 2. Let's go to the very beginning. Okay, this is a new one. So process 2, it first send a message, say M1. To say it receives a message from itself, process 2 M1, and later it receives another message said, hey, M2. But process 1 only receives the second message. Process 2 say it's 2. It doesn't receive the first message. Process 2 send a multicast. So it will lead to one issue. Let me explain that. Process 2 say it's 2, but my knowledge, process 1's knowledge of process 2 is 0. 0 plus 1 is 1. Doesn't equal to this 2. That means it doesn't meet the updating requirement. That means this message will be buffered. No updating, no delivery. This message will be buffered. So didn't update, just like this. And then it will send a message, it will increase itself by 1 and read more message from process 3. It update process 3 and deliver that message, update the process 3, and read one more message from process 2. Process 2 say M3, but we know it's only 0. So 0 plus 1 is 1, and equal to 3. So it cannot meet the updating requirement. That means the one more message is buffered. So I think you can guess what will happen in future. That is, it never updates the its knowledge of process 2 until it receives the process 2's first message. And later it will, we can just go to the last one. We can see the buffer, message buffer is process 2 says 2, process 2 says 3, process 2 says 4, process 2 says 5. It's never update process 2. That means this is because when I write, I don't wait and the process 1 never received the first message process 2. So all other message received from process 2 doesn't meet the updated requirement. They are all buffered. Okay, so this shows one linear situation for FIFO, and yeah, that's it. Let me stop there. So if you want to avoid this, this failure, you can just ask it to wait for 2 seconds before sending multicasting message. And if you don't wait, some process begin working fast and some process begin working slowly. So they will miss one message. That's it for FIFO ordering. And for casual ordering, almost everything are same. So you can see the main function. They have socket and change configuration and some helping method to do that. They are also same and data structures, and then 2 threads, sending thread and receiving threads. They're almost the same to the FIFO ordering. There are only one different. They are all same to FIFO. The only different is that the updating rules. That means after receiving message, the updating rules is different. So it will check more things. You can say I have a for loop. It will check the received clock vectors. And it will check the message here. So it will go through all elements of this clock vector. But in FIFO, it only check one element. In casual ordering, it will check all elements, actually, except 2 elements. It's its own message. That is, it will check all elements of the clock vector except 2 elements. These 2 are itself, because if you are yourself, you don't need to update. And the second one is who is the sender. The sender process, you don't need to check because you for the sender, you of course you trust the sender's message and you update your knowledge of that sender's clock. And when you update your knowledge of other process, excluding these 2, and it will compare whether it equals to local clock plus 1, local knowledge plus 1. So I use this if and big for loop to check whether it meets the requirement. If it meets, and then I deliver message. If it doesn't meet, we adjust the bufferage. So this is the casual ordering. But the main difference from FIFO ordering is the updating rules. After receiving a message, whether you meet the updating requirement, whether you update the message or your buffer message. So that's all parts for the multicast ordering. So I just summarized quickly that to make it more easier to understand, I split 2 parts, that is multicast programming and multicast ordering. So at first, I implemented the multicast programming to help you to, and I also show how it is different from the peer-to-peer socket programming. On top of that, we change the ordering parts. We focus on the ordering algorithm and implement them. Okay, so that's this project. I hope this video helps.